Okay, this is the introduction to confidence intervals. This will be page 116 of the notes and page 119. Page 117 and 118 are not necessary, so we will be skipping those. So we'll be doing page 116 and page 119 in the notes. So the reason we collect data is we usually don't know something about a population. Are forced to take a sample to use a proxy or estimate of the population parameter of interest. And that's what a confidence interval is. We're taking a sample and we are using that sample to make an estimate or claim about the population. Now, you all have seen confidence intervals. We haven't run them, but you've all seen them. And basically, whenever you've seen during the election year, someone has 43% of the vote, plus or minus 4%. That 43% plus or minus 4% is a confidence interval. So that's what we're going to learn how to do, but that was for proportion. We're actually going to do it for means because that's what we're studying right now. So we're going to do confidence intervals for means. We'll do confidence intervals for proportions in about a month. So basically a confidence interval says, hey, we really don't know what the sample mean. We don't know what the population mean is. So we're going to take a sample and we're going to get a sample mean, and that sample mean is the estimate of our population mean. But the question is, well, how good of an estimate? Well, that's what a confidence interval tells us. If I create a 95% confidence interval, that means I have a range of values, and somewhere in that range, I'm 95% confident the true population mean lies. So that means there's a 5% chance that it's not in there, because if there's a 95% chance that it is there, then there's a 5% chance that it's not. So the confidence interval for one sample T is we have essentially estimate plus margin of error. And really the way I'd like to start off is just saying, this is the formula. All right. Well, X bar is our sample mean, so you know how to calculate that. S is the standard deviation of the sample. N is the sample size, and T star is how many standard deviations it is from the mean. Now, there's several things that we're going to need to talk about. First off, this part of the equation is known as the margin of error. All right, it's the margin of error, and it tells us how far we think the true population mean might be from our estimate. Our best estimate is the sample mean. So this is our best estimate, and it's the sample mean. So the margin of error says the maximum distance we think it's going to be for a given confidence level. So that part is known as the margin of error. Then we also have a second part that we need to talk about, and mainly you just need to know that this is known as the standard error. So standard error is the sample standard deviation divided by the square root of n. Margin of error is when we multiply it by the T star. Okay, so there's several things that we can claim when we do a confidence interval. First off, we're 90% or 95% confident or 99% confident the true population mean lies within a specific interval. And you're like, well, I'd like to be 100% confident. So would I. But because we're using a sample, we will never be 100% confident. The only way to be 100% confident would be to carry out a full and complete and accurate census. If we're able to survey everybody, then we can be 100% confident. Otherwise, we'll never be 100% confident. So in reality, we're not going to be 100% confident. We just have to deal with that. So we're going to be some level of confidence, and a lot of that's going to be determined by the sample size, because as we increase our sample size, our margin of error decreases. And so we have a narrower window. All right. Another thing we can say, and I love this phrase, in repeated sampling, we expect this method will capture the true population mean 95% of the time, or 90%. What we're really saying is our method is so good that we know that it works 95% of the time. But that's also an acknowledgement that it doesn't work 5% of the time. Now, can we increase it to 99%? Yes, we can. All right, and we will be looking at multiple different widths or confidence intervals and different confidence levels. Things we can, I'm going to start with can claim, and then I'm going to go to cannot claim. We can claim 95% confident that it lies within the interval. Of course, we could also claim that we're 5% confident that it doesn't lie within the interval. It's an acknowledgement, whatever we set that at. If we say 99% confident that it lies within the interval, then we're 1% confident that it doesn't. And we can also say that if we did this over and over again, or 99% of the intervals collected will capture the true population mean. It also means 1% of the intervals we collected using this method won't. What we cannot claim 95% of the values lie within the interval. It's possible our interval is just plain wrong. It's also possible that we have something that looks like this, a data or a parabola, in which case the mean is here and we don't have a whole lot of data lying within it. All right. We cannot say 95% chance that a randomly selected value would lie within the interval. Our interval may be wrong, and we don't like talking about chance. We don't like talking about probability when we're talking about confidence intervals. Please just stick to the term confident. We don't like to say likelihood. We don't like to say probability. We don't like to say chance. So please don't use those words. Only use the word confident. 95% of the samples will result in this interval. The fact of the matter, every interval is going to be different. Every interval is going to be different. So consequently, 95% of the samples will not result in that interval. Every interval will be different because every sample is different. And the last one, 95% probability that the true population mean lies within the interval. We hate the word probability. We're 95% confident, so please stick to the word confident. Do not use probability, use confidence. I don't know what else we can say. Please note, this is a huge star, a huge star. We are making a claim about the population mean and not the sample mean. Why? Well, we just calculated the sample mean. We calculated the sample mean when we did this, so we know the sample mean. We're 100% sure that the sample mean is in there. Matter of fact, sample mean is the center of the confidence interval every single time. So we know that we're making an estimate or claim about the population mean. We are 95% confident that we captured the population mean. We're 100% confident we captured the sample mean. Also, as we increase the level of confidence, if I go from 90% to 95 to 99%, the margin of error will increase, which means the interval gets wider. The margin of error will increase and the interval gets wider. This is also really important. As we increase alpha, the margin of error decreases and our confidence decreases. And you're going, well, you haven't even told us what alpha is, so let me do that. So a confidence interval is centered about the mean, and let's just say we had a 95% confidence interval. If we had a 95% confidence interval, this would be my lower bound and this would be my upper bound. The alpha equals the area in the tails. Alpha equals the area in the tails. So you could calculate it by going 1 minus the CL. So 1 minus 0.95 equals 0.05. All right, so we have 0.05 area in the tails. So in this case, alpha equals 0.05. Well, this area is half of that, so that's 0.025. And this area is 0.025. Those combined together give me my alpha 0.05. So alpha is just in the area in the tails. All right. As the sample size increases, the margin of error decreases. So if we want a narrow confidence interval, if we want to narrow our confidence interval, increase the sample size. So increasing the sample size helps a lot. Okay, we're going to skip page 117 and page 118 and move over to page 119. And again, we're still doing the introduction of confidence intervals. And I kind of just have this chart to give you an idea of what a confidence interval looks like. All right. So we said the population for the confidence intervals in the chart is highly skewed, but the sample size for each confidence interval is 50. So consequently, even though it's skewed, because it's greater than 30, central limit theorem applies. All right. So therefore, it becomes normal for the distribution of the sample means. The sample means distribution is approximately normal for each confidence level. And if I had a Z, now we're going to primarily be working with T's because we rarely know the standard deviation of the population. So if we're working with the T, it's going to look like this. T star S divided by the square root of N. Once again, we rarely know the standard deviation of the population, so we have to use the standard deviation of the sample. But for this example, I'm going to use the Z. So I'm going to calculate a Z star, and basically I'm calculating a 90% Z star. And the way I'm doing that is second vars, inverse norm, parenthesis, 1 minus 0.9, close parenthesis, divided by 2. Mean is 0 because this is a Z standard deviation of 1. And I end up getting 1.645. All right, so I get 1.645, and just always make it positive. All right. So here's the thing. Because we know the population mean, this will never, and the population's not the population mean, the population standard deviation, it will never vary, and all of our intervals are going to be exactly the same size if we have a sample size 50. So this number's not changing, that number's not changing, and we set that to be 50. So every interval has the same width. Well, if we let this line represent the true population mean, and these are intervals, some intervals are close to being centered, like this is close to being in the middle. Some of it barely capture it, like this one barely captures it. And there are 20 of them, and it turns out 90% of the time we expect to capture it, which means 10% we don't. All right, or we would expect to. So if we did it 1,000,000 times, we're likely to happen. So 2 out of 20 equals 0.10. So if I did this 20 times, I would expect there to be 2 that don't capture it. But I'd also say, you know what, 18 out of 20, 90% of the time, I would expect to capture it. Now, the fact of the matter is 20 is a relatively small number, and we'd be better off if we'd done like 1,000, and we'd be much closer to that 90% level. But this is for example. Now, when I go to the T distribution, which is what we're primarily going to be working with, and I'm still going to keep a sample of size 50, our standard deviation is coming from the sample. And every time we do take a sample, we're likely to get a different S. Consequently, even though this T star is not going to change and this N's not going to change, our sample's standard deviation is going to change. And sometimes it's going to be wide and sometimes it's going to be narrower. And that's why we have intervals of different widths. All right. So let's go ahead and calculate a T star. So second vars, inverse T, once again, parenthesis 1 minus 0.90, because we're going to do a confidence level of 90%, divided by 2. And our degrees of freedom, in this case, is just going to be 50 minus 1, or 49. And we end up getting 1.677. So that's where the 1.677 comes from. And once again, for every sample of size 50, this will be my T star if I want a 90%. I'm setting it at 90%, and this at 50, this will be 1.677. But S can vary. But once again, this is a 90% confidence interval, so 90% of them should capture the true population mean, and 10% will not capture the population mean. Sure enough, when I drew this, I forced it. I have 2 out of 10, or 10% that failed to capture it, and I have 18 out of 2 out of 20, 18 out of 20, or 90% that did capture it. Once again, the more of them I do, the more closely I will be to the theoretical. So that's the introduction of a confidence interval. It doesn't say that it's going to be, it doesn't say the mean is going to be exactly in the center. It just says that we're going to capture. We may barely capture it, all right? And if we have a 90%, we're going to barely, we will capture it 90% of the time. I'm not saying where, but 10% we won't. If we have 95%, we're going to capture it 95% of the time if we do it over and over, but 5% of the time we won't. So that's kind of the idea of a confidence interval, is it gives you some idea as to where the actual population mean might be based on our sample mean. Once again, as our confidence level increases, our margin of error increases and the interval increases. If we increase the sample size, our margin of error decreases and our interval decreases. All right, so that ends that video. In the next video, we'll actually run some scenarios.